kind of an overview. This is, honestly, at this point, kind of old info. This is the paper based mostly on the presentation I gave either in the winter or spring. And this is going to gloss over all of it in a lot less detail because it's only 5 minutes. Hi everyone, I'm Matthew Hunter. My advisor, Professor Simone D'Unico, and we work in the Space Rendezvous Lab at Stanford University. And my paper is entitled Closed-Form Optimal Propulsive Differential Drag Control for Reconfigurations of Spacecraft Swarms. In general, distributed space systems offer many unique capabilities over monolithic satellite systems, advanced science capabilities, as well as design redundancy through often similar construction between spacecraft. However, using the smaller spacecraft, often typical in distributed space systems, often leads to hardware constraints on computational power and onboard fuel. One such mission that's the focus of this work is SwarmX, which will be a distributed space system taking distributed space weather measurements in a novel 3U CubeSat LEO swarm, and will require over 1,000 kilometers of change in a long track separation, over 15 to 450 orbits. And the mission itself is not feasible under the limits of a 3U CubeSat propellant. So to meet this problem, I'm proposing a propulsive differential drag hybrid control approach, where atmospheric drag is leveraged on board the spacecraft by modulating attitude to create differential drag between the spacecraft and the swarm. Using the negligible cost of delta V cost of differential drag and balancing it with the control authority of propulsion to achieve the final state designated control window. And this approach must be robust to large reconfigurations and extended control windows typical that we might see on SwarmX. My approach for this solution is to use the parameterization of relative orbital elements to produce a linear time variant model of nonlinear dynamics, and to partially decouple the in-plane or radial tangential motion from the out-of-plane motion, or radial normal. I paired this parameterization with an application of reachable set theory, which provides a geometric way to identify analytical minimum costs and optimal maneuver times for the reconfiguration, and also allows us to partially decouple the propulsive problem from the drag problem to find a mutually optimal solution for both for the hybrid control problem. And this process is illustrated in the top right, where we have set S, which is a set of all single maneuvers of an arbitrary magnitude of the control window, and set S star, which is the convex hull of these maneuvers. Various consistent contours of the propulsive reachable set dictate the minimum cost for the overall in-plane reconfiguration. And matching the direction, or the direction of the outward normal, the supporting hyperplane of these contours, with the drag reachable set, provides the optimal differential drag profile to pair with this optimal propulsive differential drag, optimal propulsive differential drag solution. And this way we're able to solve both problems simultaneously and in closed form. And the result, back at the bottom left, is a robust closed form architecture. The hybrid subproblems are solved sequentially to minimize coupling effects between the drag problem, the out-of-plane control problem, and the in-plane problem. The fewest maneuvers are used for both differential drag control and propulsion that allow optimality and controllability to preserve onboard memory. Near optimal solutions are provided for large along-track reconfigurations where no optimal control solution is possible within the closed-form solution architecture. And the full algorithm runs in linear time by identifying the most efficient propulsive maneuvers a priori. So down here you can see the basic solution approach for the propulsive solution, which just requires a simple matrix inversion, given an optimality constraint and the relative effects on the ROE that do not dictate the minimum cost of the configuration. The differential drag solution is simply just a combination of all possible variations of the optimal differential drag profile found by reachable set theory. To validate this approach, the validation reconfiguration considers a large change in a long trek separation over 100 orbits. And it demonstrates that the proposed algorithm finds the correct optimal cost for each subproblem and matches the final state error of numerical approaches at a fraction of their runtime. So in summary, the significance of this work is a complete framework for perfectly optimal hybrid DSS maneuver planning that's usable in a wide variety of LEO missions. And the reachable set theory approach in general is applicable to any generic impulsive continuous control problem with LTV dynamics to guide the creation of future closed-form solutions for arbitrary systems, and demonstrates the ability for a single methodology to analyze optimality for multiple forms of control. Thank you.